Welcome, everyone. This should be for all of my classes for the week of May 4th through May 8th. I'm combining these two because I'm going to do the same section for both classes, and it is section 6.2, which is on exponential growth and decay. The reason I've chosen this one, we've been pretty much doing a lot of linear equations, linear inequalities. Secondary Math 1 is really linear functions and exponential functions. So we need to spend I want to spend a little time with exponential functions and review that and go over that with you guys. Thanks for tuning in. I know this again is kind of difficult to do, but I appreciate you guys watching this. Again, kind of same thing. I'm going to go through with the computer and show you guys on the ebook what you guys should do for this section and take a look at some of the examples, and then I'm going to come back to the whiteboard and give you guys some other examples and go over a couple of problems from the actual assignment. All right, let's take a look at the ebook for this, which is going to be on page 282. Remember, we're dealing with section 6.2 this week, and only the one section. There's a lot with this one, and it is on exponential growth and decay and a few applications for it. All right, the generic exponential growth equation, and I'll go through this on the whiteboard with you guys also, but it is y is equal to a times 1 plus r raised to the t power. This is exponential growth. And y is your outcome, your final amount. A is your initial value that you're starting with. 1 plus the r, in this case, if it's 1 plus r, that is the growth factor, how much it's above 100% increasing. And t is the amount of time. So they walk you guys through a couple examples here. And again, they give you a tutorial here with the right arrow. So please take a look at that, follow that one. It is a very good example. It'll walk you through a pretty straightforward exponential growth. Okay, on the next page, we're dealing with exponential decay. And on exponential decay, it's similar. There's only one slight difference, and that is, in this one, it is going to be the same. Y is equal to A, output, initial value. But in this, it's going to be one subtract your rate of decay. So this means something is going down by a certain percentage. So if something was going down by, let's say, 3%, okay? So suppose a population was going down by 3% every year. Then this would be 1 subtract 0.03. And remember, 1 subtract 0.03 would be 0.97. So in class, what I tried to emphasize with you guys is if it was a 3% decrease or decay, that would give you 0.97 here. What that really means is that you're retaining 97% of whatever it is. All right, so for this one, again, that is your generic equation there for exponential decay. All right. Then they walk you through a couple problems where they give you a table, and in this table you're trying to see if it represents exponential growth function, an exponential decay function, or neither. The way you test that is you're looking at the change in x here is just going up by 1, but it's this change in y. So 270 down to 90, you're dividing by 3 here. And they're going to show you here that it's really multiplying by 1/3. Remember, dividing by 3 is the same as multiplying by 1/3. Same thing here. It goes down by 1/3. It goes down by 1/3. So this has an exponential decay function. Because again, it's going down by 1/3 every time. Every time going down by 1/3. This one right here, your x is going up by 1, and your y value, notice this, it doubles every time. Multiply by 2, multiply by 2, multiply by 2. So this one would be exponential growth. Exponential growth. All right, and they give you guys a couple examples down here with the monitoring progress. Please check those out and see what you're doing with those. But
I guess let me just give you a quick one on this one. If you look at this one, your x's goes up by 2 every time, and your y values, they go up by 7, by 7, by 7. That's a constant rate, but notice you're adding. When you're adding or subtracting every time, that ratio's the same. Remember, that would be a linear function. This one is not. This is not asking for if it's linear. This would have to be an answer of neither. It's not exponential growth or decay. This one would be a linear function. Okay, for exponential growth or decay, you have to multiply or divide by the same thing every time. All right, if we go to this next page, this has some examples for you guys on how do you determine if it's exponential growth or decay and then identify the rate of change. So for this one, the initial value is 5. And this one, since this value is more than 1, it's more than 1 by 0.07. This would be a 7% growth. 7% growth. This one, your initial value is the 0.2. This value is less than 1. So a lot of people on this would say, oh, it's a 98 or a 0.98 rate of decay. Be careful. I just want to emphasize this. This is not 0.98 or 98% decay. This one would be, remember, it's 1 subtract R. So this one would be a 1 minus 0.02. And it does show you that right down here, which means it's a rate of decay of 2%. I know you can see that one as a tutorial, but I just want to emphasize that one for you. All right, then we come down here and we have compound interest. I'm going to take a look at this on the whiteboard with you. We looked at several of these in class. In fact, I spent an entire day. I really think compound interest is a valuable one that for exponential growth that comes up often, and it's going to affect you guaranteed sometime in your life. So for this one, here was your general equation. I used B for balance when we did it. But the thing you've got to notice on this is N is the number of times it's compounded per year, which could be, again, 1 annually, 2 semi-annually, 4 quarterly, 12 monthly, 365 daily. And then you're going to multiply it by how many times it's compounded per year times the number of years. And if you go to the next page, they walk you through an example on that one. Okay, you have $100 in savings, so that's your initial value. 6% as a decimal is 0.06. This one's compounded monthly, so that's why you're dividing by 12, and you'd raise it to the 12 times t. So they kind of end here with this one, but if you extended this problem out, suppose you had your money in there for 8 years. Then you would do the same exact thing, and at the end you would take your calculator and you would do 100 times 1.005 raised to the 12 times 8 for 8 years. That'd be 96. So you'd raise it to the 96th power, and that would give your balance after the 8 years. All right. Do not worry here, guys, about example 5. All right. I just gave you problems up through example 4 on this. That is plenty of work to do. Thank you. Hope you listened all the way through on this. I'm going to do some examples on the whiteboard for you guys. And that should do it for this week.